Well, next presentation is going to be Franceli do Carmo Silva. She's a PhD student at the University of Campinas. PhD student at the University of Campinas, and she's going to talk again about lattices on some algebraic lattice scope constructions. Thank you.
So good morning to everyone. First of all, I'd like to thank you to the organizers to accept this invitation and for the opportunity to present here. As Sarah presented, my title is about some algebraic lattice-scope constructions. So first, we'll present some motivation to study this kind of lattices, and then some preliminary results. And finally, in the third moment, I will present a construction that we are trying to propose. And when I'm talking we, I mean my supervisor and Professor Grazielli. And finally, I will present the main reference for this work. I need to anticipate that this is a work in progress, so we just have some partial results. We didn't finish to study everything about these constructions. So the first question is why lattices? Why should we study this kind of structure? And besides the algebraic properties of these structures, we also have a lot of applications of lattices, mainly in two areas. That is in information theory and in cryptography protocols, especially for post-quantum cryptography or lattice-based cryptography. And in a theoretical perspective, lattices also combine geometric and algebraic properties in a good way, let us say. In another way, when we look on lattices constructed by linear codes and also sometimes using algebraic number theory, we guarantee a lot of good properties in terms of invariance of the number field that we are considering, and also in general, this kind of lattice may admit efficient coding and decoding process. So our goal is to consider what we call generalized checkerboard lattices that generalize some well-known family of lattices, denoted usually as GAN, to characterize this construction, that is construction B lattice. I need to say that this construction was studied before by some different authors and in different directions. So we have construction B lattices for residual integer rings, and also for some kind of principal ideal domains, especially for Eisenstein integers and Gaussian integers. So our definition of lattices here is a little bit different from the definitions that Karina and Grazielli presented. Here we are fixing a number field K that has degree n, and whose ring of integers is denoted as OK. So for us, an OK lattice or a model lattice is a finite generated OK model in the space Kn, or usually we can adopt the Krn, that is the tensor product between the number field and the reals. This structure is used especially to ensure that our lattice can admit a geometric interpretation. So the rank of this lattice is defined with respect to its model structure, and when the rank is equal to n, that is the dimension that we denoted here, the lattice is said to be a full rank lattice. Notice that if we choose k as the rational numbers, then we recover the previous definition of lattices that for us will be called as Z lattice. But in general, if we consider OK lattice, we don't have necessarily a basis for our lattice. This occurs because in general, for representation theory, we can prove that a finite generated model is always represented by a finite sum that is composed by vectors, that here is denoted by B1 and TBR, and some fractional ideals that I denoted as I1 until IR. So for us, the set of these vectors B, that is a basis, a fixed basis actually, for KRM, and the set formed by the fractional ideals compose what we call a pseudo basis for all lattices. So here is the classical examples. So if we take particularly the entire ring of integers, we have Z2, for instance, the Cartesian product actually, and the hexagonal lines up to isometry that correspond to the Eisenstein integers. There's an interesting connection between Z layers and OK lattices. Precisely if we fixed some kind of embedding that goes from our number field to the real space, we have a correspondence between OK layers and Z layers, but with different dimensions. So if we fix the OK layers with dimension n, then we can obtain Z layers of dimension n times little n on the little, where the little n is the degree of the extension. Here we are focused more in the twisted embedding that Grazielli already told us about. So the most common construction of layers by using a code is the so-called construction A layers that is obtained precisely when we fix the linear code over the ring obtained by the quotient of OK by a fixed ideal A. And then we take the preimage of this code and we call this as lambda A of C, and we call as construction A layers. Particularly if we fix a prime ideal, we have codes over finite fields. However, in general, we just have that these codes are always defined over Frobenius ring, which allows us to guarantee a lot of good properties from coding theory, especially regarding the cardinality of these codes. Here is a classical example. But another question is that if we can adapt this construction in order to have lattices with other properties. So to illustrate with an example, if we consider this binary code generated by 1, 1, then the construction A reproduces some copies of this box, where the construction B that I will introduce in the next slides is given by this picture, the reproduction of copies of this box. So precisely what we are trying to do is considering the original code and just select some code words in the first box, so in the first binary box. And then we consider translation of the previous code word that were not considered before. So in general, the construction B for residual integer rings can be defined actually in two different directions, as I said. And this is what we call version 1, that is based on the thesis of Grazielli. And here we fix Q and we write the factorization of Q in terms of the prime 2. We only consider codes whose sum of coordinates of its coordinate is divisible by 2r. And then the associated construction B layers is precisely a sub-layers of the construction A, where we additionally impose the restriction that the sum of the coordinates of the layers vectors should satisfy the last condition. Another way to generalize this, based on other works from other authors, consists in consider codes such that the sum of coordinates is divisible by Q, while the sum of coordinates of the layers vectors are divisible by Q squared. In general, for ring of integers, we will do a similar approach, most focused on the first following the first version, a construction B layers as this sublayers of construction A layers, where the codes were satisfied the first condition. So the sum of coordinates is a multiple of the even part of the ideal, while the sum of the coordinates of the layers vector satisfies this condition. Here we have some examples. We could also define a similar approach to the conversion. So instead of considering the even part and the odd part, we could only consider the entire ideal A and the square of A. And then we have a difference, explicit difference between these two constructions. We are more interested in to study the construction B1, let us say, because in most of the case, the second version provides just a sublayers of this main version. So the connection with check-board analysis is presented for binary construction B that were well studied by other authors. And here what we do is precisely to define generalized check-board analysis in order to have a similar behavior that we had in the case in the binary case. So precisely in the construction B over residual integer rings, we'll have that here the n is a sublayers of construction B, and the cardinality defined by these two layers is related exactly with the cardinality of the code. So here we define the check-board analysis as the layers defined by this the solutions of this congruence, a mod a fixed ideal S. For instance, we can consider Eisenstein and Gaussian integers. And our main result is that we can always consider a scalar version of the checkerboard layers in order to have that this is a sublayers of construction B, provide that the fixed S layers is such that our ideal fixed A divide S. Also, we have a similar behavior as before. We have that particularly A times this generalized check-board layers is a sublayers of construction B, and the cardinality defined by them is exactly the cardinality of the code. However, we have a restriction here that is precisely that the A unfortunately, we cannot remove this restriction. We can prove that at least in the way that we state this result, this is a leaf alone leaf. So we really need that the even part is a radical ideal. However, even though this can seem kind of a big restriction, we have a list of examples of number fields where this for sure occurs. So, for instance, if you can prove that there are not prime ideals above 2 that divides A, which means precisely that the norm of this ideal is not divisible by 2, then for sure we have that the previous condition is satisfied. Also, if K is a Galois number field and the 2 is taken as the radical of 2OK, we also have that the result holds. And finally, if 2OK is totally ramified, inert or unramified, then we have that the proposition also holds. I'd like to finish, present a brief overview of the geometric interpretation that I commented at the beginning. So, so far we just have considering the construction B layers as algebraic objects. However, if we equip KRM with a bilinear form, usually asymmetric bilinear form, but not necessary, we have some geometric invariants associated to our layers. So here, the most common choices are the emission inner product and what we call the twisted trace pairing that is defined by the trace of the extension by using a twisted positive element. So now we can interpret our layers not only as finitely generated models, but as pair formed by the model and the bilinear form that we are using. In this sense, we can define an invariant that is kind of the grand matrix of the lattice, and we can study this structure. So basically, we provide a closed expression for the grand matrix by using the emission in a product that's related with this matrix B. And with this result, we can provide an expression for the volume of the lambda B1 of C in terms of the volume of the checkerboard lattice scale by this ideal. So we have a lot of open problems yet. The first one is that, as I said, construction B is always a sublattice of construction A. So we'd like to explicitly give the index between these two lattices. We also like to characterize better the geometry of construction B lattice, not only as model lattice, but by using the twisted email. And finally, we'd like to provide some extension by using not necessarily rings of integers, but also maximal orders over some algebra, in general some semi-simple algebras, or even more some Dedekind domain, because we have also this definition of lattice over Dedekind domain, but we don't have this kind of construction yet, to the best of our knowledge, in this context. So that's all. This is the reference, the main reference actually. Thank you all for your attention.
Questions? Comments? Thank you.
First of all, thank you for your really nice presentation. And could you tell me more about what are the possible applications in information theory and cryptography?
Oh, yes, sure. So for information theory, exactly construction B has been studied mainly for application in quantization. So some authors proved that construction B behaves better than construction A, also in doing to the decoding process. So for information theory, I would say that the main motivation is this one. While for cryptography, for instance, we particularly have an interest to study how isometries behave between this family of lattices. So precisely if we can characterize construction B lattices that are isometric, and this kind of problem is well studied in cryptography recently due to the lattice isomorphism problem that is that has motivated a lot of cryptography protocols.
More questions, comments, suggestions? You have time.
Another. Do you have any intuition about what the cardinality of the quotient group would be when combined construction A and construction B?
Oh, yes. Well, I didn't prove yet, but since in the residual integer rings we have that this cardinality is equal to 2, I conjecture that this cardinality in the general case should be related with the norm of the even part. So I conjecture that is precisely the norm of the even part.
More questions? No, I mean, I was thinking. You say there certain simple algebras. Why? I mean, why certain? Is there any problem with them or something with all of them?
Yes, the main problem is that we need to induce a symmetric bilinear form by using a fixed algebra, and it's proved that it must be a semi-simple separable algebra over a totally real number field in order to guarantee that the symmetric bilinear form induced by the reduced trace over this algebra is well defined and positive definite. So, use the main result.
No more questions? Thank you. Have 5 minutes. Next
Nice 5 minutes before. And I won't use my phone. Well, I may just put it there sometime
I mean, we have,
She will tell me.
we still have 5 minutes.
No. Unless people request me something to be written on the board, but I didn't take a chance. Never knew. I just arrived. Summer for us. Yeah, because I like cold temperatures. But they say it's a bit unusually cold.
I have to take off because I'm going to Bali next month. By the December, I will be
Yes.
I will.
We know we're good. I know we're surviving.
Everybody knows.
Is there a pointer?
Our last talk this morning is going to be Professor Claude Draper.
Yeah, that's okay.
Non-binary codes and quantum entanglement. Thank you.
Thank you. Hello, everyone. Thank you for the organizer to let me chance to be present. One of my, should say, rebooted research area that I haven't touched for a few years, but I'm going back slowly into it. And it's going to be about error corrections, but mostly in the non-binary world, and quantum entanglement. So my PhD thesis was about basically solving a conjecture by Bell in 1964 on the simulation of quantum entanglement. And it was 2012, and I didn't touch it after. And I started to do Daniel, and because of Daniel, I started to do a lot of finite fields. It's like maybe I should think about something other than binary things and new fields and higher characteristics. So that's it. And Toronto Metropolitan University changed name after I arrived. Before, for those who don't know, it was called Ryerson Polytechnic Institute. Okay. So the big plan today, I discussed a bit of qubits, so which are the non-binary analog of qubits, quantum codes and finite fields, the error correction concepts. I'm not going to discuss about algorithms to encode, decode these things. I don't have time. And where I want to go, the entanglement assisted code. Okay, and present you some examples of why it's interesting to have entanglement in the codes. Originally, codes, those mostly like the short codes and Calder-Bank codes, were not entangled. They were not using entanglement, which is a fundamental resource of in quantum physics. Okay, it came later, mostly a paper due to Todd Brown and Marcus Gressel. So. Qubit systems, quantum codes, and finite fields. So Marcus doesn't like my definition, but I'm still going to take it, okay? So it comes from a textbook, and I just like it because for the audience here, it's quantum field. It's finite field oriented, okay? But usually a code, what it is, it's a subspace of a vector space or modules, which can be even a subspace of a larger space, which is called the ambient space, okay? But here for us, Calder-Bank shows that going from the vector space or linear space algebra to there's a motivation. It's the work of Calder-Bank, okay? So I'm starting from this definition here. And so we start with a Fq² as a symplectic two-dimensional space, okay? And a non-degenerate bilinear form is simply if all the vectors are isotropic. Okay. So, and what is a code? I use double bracket. Okay. So we have a code with the ambient space and dimension k, and distance d is a q-linear q² array subset of e to the n, which is the space. Okay. So the Cartesian product of that times n times. Okay. It contains its joule, and every word has weight not in the perpendicular and the joule of the code, has weight at least d. Okay? The code is pure if all non-zero code words has weight at least d. Okay? So a few remarks. N plus k over 2, this is how it's needed. Is a q square array dimension. The code C as q to the n plus k words. An extreme case is when k equals to the ambient space, then with dimension equals to 1, we have that code, okay? The other extreme is when k equals 0, in that case the joule equals to the code. And a pure code, as I said, this is just rewriting what I gave on the previous slide, okay? Can be seen as a classical code. Here, this is classical, okay? One bracket, sorry, this should be a square bracket here. And the classical code associated with the stabilizer code, I'm not going to really touch stabilizer code here, is only assumed to be additively closed. Okay, so it's FP linear. And this case of Q linear, Q square array codes is just one special case, but it's pretty much all what we need to do error corrections, following the work of Knil and other people. Okay, so from classical to quantum, if we start with classical code over Q square, okay, the field of SQ square, the quadratic field extension, containing its dual with respect to the Hermitian form, then there's an FQ isomorphism between this classical code and this Q-ary quantum code, okay? And the proof took quite a while to understand. I put it in the appendix if someone wants to have the slide, but it's also in section 18.4 in the textbook, okay? And that isomorphism is extremely important actually to build connections between classical codes and quantum codes. So duality can be based not only on non-degenerate bilinear form, but also non-degenerate cisquilinear form, such as the Hermitian inner product. Ashmin, sorry for the name, Knil gives a physical justification for this theorem. Okay. Knil is the one who established the conditions under which a code can correct quantum errors. Okay. So an example here, if we take F4, okay, we have the check matrix. In F4 we have this. We can reduce, rearrange, and put it in the normal form, and have this form. So it's a classical code in F4, self-dual with respect to the Hermitian form, okay? If we use a previous theorem, then we get it's also a quantum code. It's not an interesting example, you're going to say, because the rate is 0, k is 0, but it's just to give you an example that fits in the theorem and fits on the slide as well. Because I have other examples, like it looked like 3 slides. Then that's one of the basic examples. Okay. So now what are qubits? Okay. Qubits is just a d-ary digit system whose state can be described by a vector in the d-dimensional Hilbert space. The Hilbert space is always finite. Here we don't deal with infinite one, where we have to deal with completeness and everything. But in information theory, sometimes you can deal with infinite dimensional Hilbert space. The Hilbert space found a set of orthogonal basis vectors. So basically the canonical vector, elementary vector. And just giving an example here, the qubits. So these vectors are orthogonal, ket 0, ket 1, ket d minus 1, okay? And it satisfies the normalization conditions, okay? One example of the quantum state using the finite fields here is this one. This is basically the tensor product of A with BA. We can think of residue here and define the states. The geodesic state, which is my favorite one, spend my PhD thesis on this one. It's a maximally entangled state, okay? And you will see why I'm mentioning that later when I'm going to talk about the entanglement. Okay? It's a highly entangled state. Okay, so actually, if you have to take one representative of maximally entangled state in the bipartite case, where we have a receiver and a transmitter, so someone transmitting information, someone receiving, not more than 2. Only in the bipartite case, this is the state you're going to choose. Okay. Okay, it's in the tripartite or more state, when you have a bigger amount of people in the network, it's not known what is maximally entangled. That's something else let me discuss later. Quantum error correction concept, qubit error basis. So we take the root of unity here. We have 2 types of errors, okay, that we like to correct. The bit flips are the x's and the phase flips are the z's, okay? We can compose them. So we may y was y, but y is just a composition of the two, so we don't mind, it doesn't matter. And we take beta gamma in the finite field. Okay, so these are the parameters of the error operators. How much time? 5 minutes.
You have 10.
10 left. Okay. Operator actions. So you may have seen those in the case of the qubit case, but the goal here was to do finite fields, so I just presented you finite field versions. Okay? They are much more easier to deal with in the binary case. And the trace here is used to define the effect of generalized phase flips. Okay. If you're in the binary case, basically you just have a diagonal with 1 and -1. You flip the wave, okay, the amplitude. So these are the error, and that's all we need to correct in the quantum world. Okay. Again, some results by Gutzman, Kindle. I have all the reference at the end. So our one qubit error is represented by a pair. The pair of parameters, so beta for the x, the bit flipping, or the qubit flips. So, and gamma for the phase flip, okay? So quantum code is a subset of, as I mentioned before, this was E basically, so I said the end of the even dimensional space over Fq, okay? An equivalent representation, so if we have a periodic expansion of B, okay, and field elements, this is just basically recalling the isomorphisms between C to some power, dimension D is isomorphic to C, where C is the complex number. Okay. These are the error operators. Okay, so we have what? A few properties. This is the basis for the error operators. Okay. And we have the conjugate transposition, multiplication, commutativity, the order of x and z is the characteristic of the field, okay, p, so I didn't say it, but q is p to some power e. I choose e here because usually we choose k for the dimension of the code, so if we choose q is equal to p to the k, it's confusing in notation, so but basically the characteristic here is p, okay. For two basis operator in the TensorFold basis BQ, okay? Let's say S1 and S2, then we have parameters for each dimension, okay, that we are working for each dimension of the ambient space, okay? So the dimension of the ambient space is n, and we have a parameter for each of the bit flippings or qubit flipping, and the phase flip, okay? The commutativity is determined by the symplectic product, which is given by this. In the case of the qubit case, the binary case, saying that the symplectic product is 1 means they are anti-commuting, okay? But the anti-commutation doesn't really make sense in fields of characteristic higher than 2, okay? In the non-binary case, so. But still, it's a measure of commutativity, okay? An example here that fits on the slides. If we take p equals 3, quadratic extension degree 2, if q is given by this with the irreducible polynomial x squared plus x plus 2, then we can have, for instance, these 4 parameters, which are actually the stabilizer group, okay, and represented in normal form. So we have to the left of the bar the x operations, and to the left the z operations. Okay, so we are fixing a qubit flip here. Okay, and here we're fixing the phase flip. So this is, again, there's a little typo here. It should be bracket, bracket, square. We have a 392 code as a 9-array qubit, standardized code. Why? I put it in the appendix. Okay, it's a long result. Okay. But here's an example. Okay, and it's used 5. Okay. So at the beginning, we have this duality containment relation. Okay. I will skip. I think you know. So the field trace mapping here is one important application of trace. Okay, we take an array, a matrix, and then we apply trace to every coordinate. Okay, with that we can create new codes. Okay, they are additive. Okay, this is a bit analogous to the kernel and the row space. Okay, of the codes of the original code. So if we take two classical code, then from out of C1 and C2, we can derive new codes that are quantum one. They are additive codes, okay, using the duality containment relation as exploited in Calderbank original paper, okay, or resource one, I think. So methods ones, okay, this is one method to get a quantum code, and the transmission rate is about this, okay. And if we use the other method using the trace map over the matrix, we get another set of quantum codes with a different transmission rate. Okay, this one is Fp linear, it's additive. This one is linear. Okay, and the transmission rate is different, as you can see. Okay, entanglement assisted is one of the best state here, and I go quickly here. Okay. Building check matrices, we have that the basis is a non-abelian subgroup of that basis, okay, with some generators, okay. So we form the check matrix by stacking the field isomorphisms. This is an example, one on top of each other. So we get the check matrices, okay. And parameter characterization, what are we looking at? Is to minimize the number of entangled resource we use, the number of Bell state, okay? So that's why probably better, as Marcus suggested me to call it maximal entanglement consuming codes, okay? Because it's really about minimizing the number of entangled qubits that we have here, okay? But in the literature, they don't use consuming code, just a maximal entanglement code. But really, the aim is to minimize C because it's expensive to build entangled qubits, okay? And using the previous construction, we have that the number of qubits that are entangled we need is given by the rank of these two, okay? Some results. This is a result from 26, a bit recent. It's a quantum entanglement assistant Reed-Solomon code, okay? And they give you the parameters we need to choose, the optimal rate, and everything, okay? And 26, it's a bit long paper, 50 pages long. And here is another example I gave. It's a tensor product code, okay? That use the isomorphism. This is interesting, and that's the thing that I want to go. Last line, most important. You have 2 zero rate code here. Quantum code, unentangled, 2 zero rate, okay? K is 0. Nothing can be transmitted here. You combine them, and boom, you get something with a non-zero rate. Zero entanglement, okay? Just remember, entanglement is powerful. That's what genuinely distinguishes classical system from quantum system. Okay. And that's it. Thank you. It has 75 slides. If those are interesting, it continues after.
We want to see.
So I made something for 1 hour. But
We want to see the references. I want to see the references.
references, future direction. I want to well, I can explain you future action in third sense. These are in chronological order and by alphabetical order of names. Okay. So 1995, Shor Caldor Bank, where he exploits this. He explains how to use finite fields here. Okay? Gutman, that I know quite well, Steen, Neil Laflamme, where they explain how, under what conditions you can correct errors and not. Okay. Marcus, this gives a physical interpretation to the qubit case. Okay. So it's good to do math, but it's good to make sure that it applies in practice. Huh? So Todd here, which is the one who came first with an entanglement protocol. Okay, he has a big book if you're interested. Okay, on error corrections. These are the papers I started to read more after like this year. Although they are old, as I said, I rebooted. I haven't touched that after 2015. So I just this year started to go back.
2087. Futuristic.
Where?
Well, 2087 the date. I think you have a typo there.
This one?
Left.
Left. No, that's okay.
Same line left.
Left here.
No, previous.
Previous, that's okay. It's just a typo here. Well, don't worry.
And that's my PhD thesis, basically. And yeah, this is a textbook, which I like because it explores a lot of geometry, which I'm not a geometrist, but quantum codes and classical stuff. So yeah, Marcus, and then interesting stuff here in her PhD thesis. She works at Xanadu in Toronto now, right next to my office. Yeah, these are the quantum LZPC. Which these are the ones that I read that I know. If you're, yeah, I can discuss more.
More questions, comments? Please.
Yep.
In case entanglement system, is there some sort of equivalence of the codes?
Equivalent to what?
So when you have a classical code, you can compare these codes and talk about some kind of distance.
Or the rate, the transmission rate.
Or the transformation. So in this case, we have some notion of equivalence.
Between entangle, equivalence. You certainly want to minimize the number of qubits or qubits that you're using. So I will consider a better one that uses fewer qubits for the same transmission rate.
More questions?
I have
Sorry, but first,
Ladies first.
I have a question in a similar direction than Darcy asked. When we have a connection between the classical codes and the quantum codes,
The isomorphisms, the QRE, Q square, yep.
yes, exactly. And then this isomorphism preserves the secret linear form in some way. I mean, there is a geometric structure that is associated to the classical code and another geometric structure that is associated to the quantum code that is also preserved in the sense that, this isomorphism is also an isometry.
I think yes, if you ask me to do it on top of my head, I cannot do it. In the textbook, the section after, they discuss about geometry for quantum codes.
Oh,
And I've seen it, but I haven't dig into the details. I have it on my laptop.
okay.
So my question is about, so you said like in the zero code case, in the quantum channel, there is no transmission happening. But,
There's zero rate, yeah.
but if I use the classical code, I can transmit something over a classical channel, right? So
And the classical, okay,
what's the intuition behind it? You said like if you entangle two zero code at the
to 08 code, yeah, and then you concatenate them, or you take the tensor product and concatenate them, okay?
What's the intuition behind it? Like
from your perspective?
Well, the intuition is that's how we use entanglement. I mean, I've seen a lot of counterintuitive things with entanglement. Okay, going on. In like if you take cryptography QKD for instance, it doesn't require entanglement. Okay, but you can if you use it though, you're gonna make your life way much more easier. Okay, same thing here. You don't have to use it. Okay, but if you use entanglement, like it's an art for me so far. Like Todd Brown when he first came with it, it's the example that I give at the end, like from Todd Brown's paper, the 2006. I was like just by a bit like try and oh that works. Okay, that's what he told me. So intuition behind maybe we can get insight using geometry actually, but I'm not a geometer, so I know some people who are doing that. Okay.
More questions?
The last one. For someone who wants to learn more about quantum coding, which book would you recommend?
About quantum codes?
Yeah.
Well, Quantum Error Corrections, the book by Todd Brown is really good. Okay. If you're a math person, you're gonna go with the book from Bauer. Okay. And then other books, there are more like papers. Okay. Okay. Yeah.
Thank you. Well, let's thank our speaker again. It's time to lunch.
Okay, just an announcement. Hello everyone. There will be two guys guiding you for restaurants now. One is Leonardo for more meat options, and one is Thiago for more vegetarian options. And I can show you the little restaurant you have here, maybe after it. And okay,